Hi everybody, hi. Mike here. I'm here to film lab, and I just wanted you to experience how creepy it is going through this. This building is so completely empty. It just creeps me out. Also, it's where administrators are, so it's got that going for it too. My kid gave me a haircut with my beard trimmer. It cost me $5. I'm here to film some labs, but let's go talk about electron configurations or whatever else we're talking about. Hi everybody, hi. We're back here at my kitchen table talking more about electron configurations. If you remember last time, we wrote the electron configuration of oxygen. And if you don't remember, go back and watch that video again. That wouldn't hurt. So what we're going to do is I'm going to make a point by trying to write the electron configuration of sulfur. Sulfur has, from the periodic table, go look it up, atomic number 16, 16 electrons. All right. So what we're going to do is now look. If you can recreate the scene in your head, you'll never have a problem figuring out what the arrangement of electrons is. So you remember that as you go along to each quantum level, n level, the number of subshells increases by 1. So n equals 1 has a 1s, n equals 2 has a 2s, and a 2p, an s and a p. N equals 3 has an S, a P, and a D. And that's going to give us enough room to fit 16 electrons in, because if you remember, an S holds 1 orbital, or 2 electrons, so there's 4 electrons. There's 10 right there, because a P holds 3 orbitals, or 6 electrons. So right here, that alone would hold 10, and then there's another S that would hold 12, and then the P would hold 6 more as 18, and then they fill like this. All right, in that order. So that's how you bulletproof your knowledge of this. And then once we get to enough orbitals to hold 16 electrons, we can then write them out, you know, and then in increasing energy. Oopsie. Yeah, look what I did. 2s, 2p. All right, and 3s, 3p. So then really all you got to do is remember what an s, a p, and a d is, and there's actually a pattern to that. 1, 3, 5, 7, they increase by 2 each time. Once again, don't worry about the y, it just happens. So we're going to pile 16 electrons into these orbitals following all of the rules, which is the Pauli exclusion principle, that the first 2 have to be of paired spin. So that's how the 1s and the 2s fill. And I'm going to go, this is going to fill, but I'm going to go and continue along. If we had, 7 electrons would follow Hund's rule, where they wouldn't pair until they have to. There's our 10 electrons. There's electrons 11 and 12. And then 13, 14, 15, 16. Now, does that look familiar? It looks like kind of like what we talked about last time, but the electron configuration of sulfur is 1s2, 2s2, 2p6, 3s2, 3p4. Let's go back in time to oxygen. Oxygen ended with a P4. As a matter of fact, let's write that right next door. Here. There's sulfur. There's oxygen. 1s2, 2s2, 2p4. From last time. P4. P4. Now, if you look in your textbook, there is a periodic table that is broken into blocks, and this is where we have, back when we first started our journey, we talked about how the columns in the periodic table tend to behave similarly. So for example, you'll find that both oxygen and sulfur have two half-filled orbitals. Their electron configuration ends with P4. As a matter of fact, everything in the same family here ends with P4. All right? And so you can say that everything to the left of it, if you went and did nitrogen, everything here would end in P3. All right? Very similar to what we were talking about. Everything here would end in P2, P1. You see the pattern, and you see why the block of these elements all end in P something. P1, P2, P3, P4, P5, P6. And so that's what happens. You have a repeating kind of feature to the periodic table, and that's why they call it the periodic table. That the saying that history doesn't repeat itself, but it sure does rhyme. Well, that's what the periodic table does. Sulfur is not the same element as oxygen, but its electrons are arranged very similarly, and that's why the structure of the periodic table exists. Okay? More on that next time. Let's do a more complex one with way more electrons next. Okay, next we'll talk about iron. Iron has 26 electrons, so I'm going to go start 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, sorry, I got caught daydreaming about what I was going to talk about next. That should handle it. Fill this way. I'm going to write them out in order of increasing energy. Okay, that should do it. So let's try to pile in to the orbitals 26 electrons, but I'm going to write them out. Remember that an s has one orbital and a p has 3, so I'm just following this order here. 3s. Now this is where things are going to get a little bit weird, but we can handle it. And then 3D. That's what I wanted to do. I wanted to get to the D. We haven't done one with a D before. All right? And the D block in the periodic table is the transition elements. That's where you can find iron. Now what's weird here, folks, is that the 4s is actually lower than the 3d. Once again, don't think about it too hard. Just pile in your electrons, okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, and then I could put that 26th electron. It's either going to choose to go up to the 4p or pair here. Now the 4p in this particular case is much higher energy than just pairing spins, so it'll go in any of these 5 orbitals. I'm just going to put it there because I like having it nice and tidy, lefty to righty. All right. So then we would write out this thing's electron configuration. It gets really, really verbose. And 3s2, 3p6, 4s2. I'll talk about this here, 3d6. Okay, couple of things. I've seen various ways where you can either have the 3d come before the 4s, even though it's in higher energy. So you might see these. Now look, folks, I don't care which one you do. They're both right to me. All right? The other thing that happens is that this starts to become very, very time consuming if you list off every single electron and what its location is. Turns out what we're going to find out next time is that what really only matters is the outermost shell. All these electrons that are in quantum levels that are filled, they really don't matter So right there, you know, that would be the nearest noble gas when that N equals 3p6, right? 3p6, that's 18 electrons, that's argon. So, as a time-saving measure, you can actually put the nearest noble gas, you can only do this with noble gases, and then you list everything that came after that to save time. So we could write 4s2, 3d6, and that's a shorter notation. This is called noble gas notation. Both are equally correct, just one's easier to do and shorter. And practically all these electrons that are in the filled shells, those are called core electrons, and they pretty much ain't going anywhere because they obey the octet rule. Now, because we're going to talk about this next time, I want to restate the octet rule again. The octet with a little bit of a twist on it. All right? And that is that an atom or ion is most stable when it has the same, when we first started, week 2 or 3, I quoted this as saying same number of electrons. I'm still saying the same thing, but same electron configuration. As a noble gas atom. All right, so iron currently is not obeying the octet rule. That's why iron can react to form other things. It's not especially unreactive. It's not as stable as it can be. That's why rust happens, and that's why all sorts of other things happen. Actually, in the transition metals, they kind of buck the octet rule. But I thought I'd get to the point. That's why we do this, folks. That's why we do this noble gas notation. We tend to talk about things in reference to noble gases. All right? So, notice, in the wording of the octet rule, I use the word ion. Next time, we're going to talk about things that aren't atoms. It could be ions. What I want you to do is look at this figure in chapter 6. And it has every single electron configuration in the periodic table. And you could try throwing darts at the periodic table and see if you could come up with the correct electron configuration. Except there are a couple weird ones. I want to talk about that next time. So do some practice on electron configurations, and we'll see you back here next time. Peace out. Bye.